In the last video, we developed the work kinetic energy theorem. And although we saw that in some cases it made things a little easier to solve, it didn't seem like it was necessarily helping a whole heck of a lot. This will start to change here as we define potential energy. So in this video, we'll define potential energy, and then it'll be in future videos when we work examples with it. So here, in order to create a potential energy function for a force, the force must be what we call conservative. So there are two equivalent definitions of a conservative force. The first definition says that the work along all possible paths connecting any 2 points is the same. So for instance, you can pick just any old two random points you like. Let's call them A and B. And what this says is that we can imagine all sorts of different paths that we could have taken going from A to B. For instance, we might have chosen to go along this path. And everywhere along here, some force will be acting on the object as we're going along. And the direction, the magnitude of the force could change. It doesn't matter. And then say we can go and take a look at some totally other path that connects A and B. Maybe like that. It'll turn out that if we calculate the work done by this, if the force is conservative, it'll turn out that the work we do going from A to B along this path is the same as the work done going from A to B along this path. And in order for the force to be conservative, it has to be the case that the work done will be the same along every possible path that connects these 2 points A and B. And then say I could pick two other points, C and D. Now, the work done going from C to D doesn't have to be the same as from A to B, but again, we have to imagine every conceivable path that could connect C and D, and it would have to be the case that the work being done between every possible path connecting C and D would be the same. Or our equivalent definition is that the work done on all possible closed paths is 0. And to see how this is equivalent, if the work done from A to B is, say, W, if I were to go from B to A, it would have to be negative W. Just because I would be displacing in exactly the opposite direction. So if the work being done from A to B is always the same, it's always W, no matter what path I take, the work from B to A would always be the same for every conceivable path between B and A, and it would always be negative W. So I could make a closed path by going from A to B and then return back from B to A. You do W along the A to B part, negative W along the B to A part. You would get 0. And so it seems like showing either of these would be an insanely tall order. But it turns out that there is a very clever mathematical construct that you can do beyond the scope of this course, but you can, there's a mathematical construct called taking the curl. And it turns out that if the curl of our force is 0, it's conservative. I'll try to give a flavor for how that sort of an argument works going on. But suffice it to say that if I tell you that a force is conservative, people have used clever math tricks to show that either of these equivalent conditions has been satisfied. So that's a conservative force. Those are hard. It's hard to show that something is conservative. However, it's comparatively straightforward to show if a force is non-conservative. And usually, but not always, our non-conservative forces are dissipative. Although they don't have to be. The thrust from a jet, for instance, is not necessarily dissipative. But probably the single biggest poster child for this is friction. So let's say you're displacing this way. Friction always opposes the motion that way. The angle between them is 180 degrees. So it turns out that to show something be non-conservative, all you got to do is either find one closed path where the work isn't 0, or you find one pair of points where for 2 different paths, it's not the same. That's all you got to do. And if you show that for even one case, then the force is non-conservative. So to that end, let's imagine taking your book and sliding it around a table. So here's your physics book. And let's say you decide to slide it across your table like so. So there's a couple different ways we could imagine going. We could imagine, say, pushing it this way through some displacement. I'll call that d horizontal. But I could also imagine, say, displacing it through here, a d vertical. Whoops. There we go. Followed by a d horizontal like that, and then return back up with, let's call that a d vertical, to end up in the same place. So we can calculate the work done by kinetic friction for both paths. So for the purple path, the work done will be the force of kinetic friction times dH times the cosine of 180 degrees, which that's -1. So this will be minus Fk dH. Okie doke. Now let's do it for the pink path. For the pink path, there's going to be 3 legs. Leg 1, leg 2, leg 3. We'll have to add them up. So the work done by kinetic friction here will be equal to, well, check this out. Here the displacement's down, but friction would have to be up because friction always opposes the motion. So the angle's still 180. This is true no matter how the force of kinetic friction and our displacement are arranged. The angle's always 180. So it'll always be a cosine 180, which is -1. So this will be minus Fk dV. Then this piece here, piece 2, will give me a minus Fk, here, let me actually just make this a little more explicit. W1 plus W2 plus W3. So W1 was minus Fk d sub V. Then work along leg 2 will be minus Fk d sub H. Then along leg 3, again, same deal. These are always 180 degrees apart, so it'll always be a minus sign here, Fk dV. So this works out to be minus Fk dH minus 2Fk dV. Well, looky there. The work done along the pink path is a different value than the work done along the purple path by a different value, by this much. So that's it. I found two paths. These are unequal to each other. We're done. Friction is not a conservative force. So, I promised I would give a bit of a flavor for showing how we can say that conservative forces are conservative. And for this one, I will take a look at gravity near the surface of the Earth. So here, you can imagine, say, taking your physics book. And it starts here, and let's just say it ends up over here. So let's say that the initial y coordinate here was y initial. The final y coordinate there is y final. My displacement here, or sorry, the change in my y coordinate here will be the negative of this height difference here. Well, it'll be negative this height difference, but we'll worry about that in a second. So let's go and again, we'll take a look at a couple different paths. Let's look at this purple path. So here, this distance d. So we can chart this out. So d is doing something like that. And gravity is the force we're thinking about here. It's got a point like that. This angle theta here. This is, angle phi here. We can say that the work done by gravity, the work done by gravity will be equal to FGD cosine phi, or MGD cosine phi. But now take a look here. This D cosine phi here. That's this bit right here. Right? D. Yeah. Oh, sorry. Yeah, D cosine phi is going to be the same as, if we call this angle here theta, this theta is 90 minus phi. So this cosine phi is the same thing as sine theta. So this is d cosine phi, or d sine theta right here. So this is our opposite. Well, either way, this d will be equal to, here we got to be careful. Delta y is going to be negative because y final will be a smaller number than y initial. So it's equal to negative delta y, or negative y final minus y initial. All right, so anyway, we figured it out. D cosine phi here, or d sine theta, is going to be equal to that. So this will be minus mgd y final minus y initial. All right, so that's one leg. Now let's go take a look at another leg. Let's take a look here at this blue path. Let's say we displace like this for leg 1, and then that for leg 2. Well, along leg 1, the displacement is horizontal. The force of gravity is vertical. That's a right angle between them. So the work done by gravity along this leg is 0. So the only other leg we've got is leg 2 here, where the displacement is straight down, and so is gravity. So here, the angle between those two vectors is 0. So the work done by gravity along this leg will be the force of gravity times the displacement along this leg 2 here, times the cosine of 0, which is 1. Alrighty. That d is this d here, this negative y final minus y initial. Force of gravity is still mg, so we get minus mg, y final minus y initial. Great. So it checks for those two. 2 down, infinity more to go. So here you might get a little distressed. Say, well, it sounds like it's going to take a while. How are we going to do this in general? So to do it in general, you make the argument, you go and take a look here and you say, all right, here's my physics book. So there's my physics book, start, finish. All right, and then what we're going to do is just imagine connecting any old random arbitrary path between these. Actually, let's use a little darker color. Maybe something like that. Now, to calculate the work done along this exact path by gravity would seem to be really ugly, but there's a trick you can do. You can approximate it by imagining a whole bunch of horizontal and vertical zigzags that zigzag around the path you care about. Oops. There, maybe something like that. And so we can calculate the work done on this zigzaggy path. Because on the zigzaggy path, any segment that's horizontal is going to be 0. And any bit that's vertical is going to be a minus mg delta y, following the same arguments we've done before. So if I add up all the delta y's over all the little bits right there, the only bits that aren't going to cancel is this much right here. So you guessed it, this bit right here. What we'll be left with is just this bit right here, minus y final minus y initial. And so then you'll get that the work done along that zigzaggy path has to be equal to minus mg y final minus y initial, just like before. But wait, you say, the path that you're showing me is curved and you just did a zigzaggy thing. Okay, fair. So what you can do is you could make the zigzags finer. Here I just drew a handful of zigzags. I could make the zigzags much finer, follow the curve more closely. And if you do it, you'll get the same answer. And you could make it even finer and finer and finer. And at some point, the zigzags will be within the width of the pixels that I'm drawing here. And you wouldn't be able to tell the difference between the path I drew and the zigzags. Now, I'm sweeping some mathematical technical details under the rug, but that is the spirit of the argument, is you can imagine making these zigzags as fine as you like, and mathematicians have shown that the limit of making these zigzags is infinitely fine, you'll still always get the same answer, in this case minus mg y final minus y initial. So that's how you do it. you can then see, you can convince yourself it won't matter what arbitrary path you do. You'll always end up getting the same result. The horizontal pieces will always be 0. The vertical pieces will always add up to minus mg y final minus y initial. Alrighty, so with that, we are finally free to define potential energy. Very roughly, the word potential here can be just kind of thought of as the potential to do work. And so we define the change in the potential energy for some force to be equal to the negative of the work done by that force as long as it's conservative. We can only do this for conservative forces because, like you see here, all that mattered was what the initial and final y coordinate was. Now, in general, it could matter what all of the initial and final coordinates were, but that's all that matters is the initial and final coordinates, because you could take any conceivable path and get the same answer for a conservative force. All it can possibly depend on is the coordinates at the beginning and at the end. So we defined potential energy just by demanding that the change in the potential energy be equal to the negative of the work done. You are actually free to choose the function for your potential energy. As long as it satisfies this requirement that the change in the potential energy be equal to the negative. So let's try this for gravity. I'm feeling really lucky, and I'll make the conventional choice for gravity that the potential energy for gravity, and here I'm just choosing it, I'll say it's equal to mg times the y coordinate. So I require that the change in my gravitational potential energy be equal to the negative of the work done by gravity. All right. So with this choice of potential energy that I made, that'll be mg y final minus mg y initial. This will be equal to the negative of, well, we found the work done by gravity was minus mg y final minus y initial. Hey, the minus signs are going to cancel out. And so sure enough, I'm going to get here, mg times y final minus y initial. And here I'll get mg times y final minus y initial. They check. So this is a perfectly good choice, and it's the conventional choice for our potential energy. However, there are other choices you could make. A not recommended choice, but you kind of do it anyway. More on that in a second. But not so recommended, but perfectly valid. Would be to say that to define my gravitational potential energy to be m times g times y plus, let's call it y sub 0, or physicists usually call that y naught. It's just some number. It has to have units of meters. So let's see if that works. So we need, again, that the change in my gravitational potential energy be equal to minus the work done by gravity. We saw for the work done by gravity that that's going to be mg y final minus y initial with the minus in front of there. So here let's put in our choice. This will be mg y final plus y naught minus mg y initial plus y naught. All right, we can expand it out. We'll get mg y final plus mg y naught minus mg y initial minus mg y naught. So we need to see if this equals mg times y final minus y initial. Well, these terms cancel. I can group on mg y final minus y initial. Sure enough, it equals mg y final minus y initial. Check. So this choice here, which like I said is the not so recommended choice, would work. I could have just some arbitrary constant, y naught. Maybe it's 82 meters. I could add 82 meters to all my y coordinates and it'll work. Now, what this really allows us to do in practice is it means that we are free to choose where we want y equals 0. Sometimes you want it at the top of the problem, but usually you want it at the bottom of the problem, unless the problem gives you some super duper clear, obvious y equals 0. They're wanting you to measure everything off of something. Well, then make that choice. I'm usually a fan of putting y equals 0 at the bottom of the problem just because it makes all of my y values positive. Nothing other than that. So you're free to choose where y is equal to 0. We'll find that that is a convenient freedom. And the reason you're free to do that is because that is effectively just adding this arbitrary constant y naught to make y equals 0, to make this be 0 where you would find it convenient to be 0. So in practice, what we do is we can choose where y equals 0. So sometimes you can do that, but other times when we do things, like say for a spring, it is beyond the scope of these videos. You have to use the methods of calculus, but for a spring force. So again, remember here for a spring force, we have a spring. This is the equilibrium position. If I stretch it to the right, this would be, this is x equals 0. If I stretch it to the right, this is a positive, and the spring force would be pushing back, pulling back. If I compress it to the left like this, this would be a negative, and the spring would be pushing to the right. Okay, and right at the equilibrium position here, where I said x equals 0, the force is 0. So we can write that the force of the spring is, and again, I'm not getting hung up about it, but we need the minus sign here just to be a little careful. Kx. So like I said, when you're doing force problems, usually what you'll do is ruthlessly ignore the minus sign and use your common sense to take care of the direction. But here we need it, and this is because if I pull to the right, that's x is positive, but the direction's to the left. If I push to the left, x is negative, but the force that the spring exerts will be to the right. So I need a minus sign just to make the directions work out. So it turns out that our potential energy function for the spring is 1/2 kx squared, where x is the stretch. And here, x equals 0 must be at the equilibrium position. So we are not free to choose where x is equal to 0. And this is for reasons of calculus. In order to come up with this particular potential energy function, for mathematical technical reasons, you already had to make the choice that the potential energy was 0 at the equilibrium position and that x had to be 0 at that point. So In the next series of videos, now that we've defined some of these potential energy functions, we will go ahead and use them to make certain classes of problems go a lot faster. Catch you in the next ones.